All right, good afternoon, everybody. Welcome back. I hope that you had a fantastic long weekend and got to do some things that you enjoyed doing. What we're moving on to today is the final lesson dealing with logarithms, which is dealing with solving logarithmic equations. And this lesson can be found on page 1 of your current lesson handout, which is part 3 of the course. And this handout takes us right to the end of the course. What we're looking at today is solving a variety of different logarithmic equations. It's a fairly short lesson, and there are two basic strategies that we are going to be using to solve equations that contain logarithms. One of the things that we're going to have to be aware of, though, to begin with, is that when you solve a logarithmic equation, you may get an extraneous root. And you should remember from previous lessons in this course and also from lessons in Math 20, that what an extraneous root is a solution to an equation that you arrive at using algebra properly, so you don't do anything wrong, but the answer you get is not valid. Now, the reason you're going to get extraneous roots when it comes to solving logarithmic equations is you are not allowed to take the logarithm of 0, and you are not allowed to take the logarithm of a negative number. In other words, when we have the logarithm of an argument, doesn't matter what base it is, the argument must be greater than 0. There's a reason for that because, for example, if I said to you, what is log base 4 of 0 equal to? I'm asking you to what do you raise 4 to get 0? Well, 4 to any exponent will always be a number greater than 0. You will never get 0 by taking 4 raised to an exponent. It's impossible. So this is not defined. And again, it's not defined because this is saying in exponential form 4 raised to some exponent gives you 0, and that is impossible. We can go a little bit further. If I told you to determine log base 4, and I'm just picking on base 4, it doesn't matter what the base is, of negative 3, that's asking you to what do you raise a base of 4 to get negative 3? And since a positive base raised to any exponent will always be a positive number, this is impossible, which means that this is not defined. So the bottom line is you cannot take the logarithm of a negative and you cannot take the logarithm of 0. And that means if you solve an equation that contains logarithms, you have the potential for getting a solution which will result in a negative argument or a 0 argument. And that means that when you solve a logarithmic equation, we have to keep our eyes peeled for solutions that we get that result in undefined logarithms. Let's take a look at the first example. Log base 6 of 2x minus 1 equals log base 6 of 11. This is very similar to the work we did when we had a common base with an exponential equation, except now they're logarithms. If I have log base 6 of 2x minus 1, and that's equal to log base 6 of 11, if the bases are the same, then the arguments must be the same. So we can write 2x minus 1 equals 11. That means 2x equals 12 when we add 1 to both sides, and when we divide both sides by 2, we get x equals 6. So how do we check for an extraneous root? We evaluate the left side and the right side of the equation with our solution that we believe is correct. I would have the log base 6 of 2 multiplied by our solution, which is 6 minus 1. On the left side and on the right-hand side, I have log base 6 of 11. Well, we can calculate the argument on the left. 2 times 6 minus 1 is 11. So on the left side, we have log base 6 of 11. On the right side, we have log base 6 of 11. What does this mean? It means that that solution of x equals 6 is an actual solution. It's correct. Take a look at the next one. This time we have an equation with 3 logarithms, but the 2 logarithms on the left can be put together as a single logarithm that's a base 7 logarithm of the product of the arguments. Remember from previous lessons that the sum of logarithms is equal to the logarithm of a product. This is equal to log base 7 of 12. And now, since the bases are the same, the arguments have to be the same. So 4x has to equal 12, which means x has to equal 3. Now what we want to do is make sure that when we put 3 in for x, we get a true statement. I will have log base 7 of 3 plus log base 7 of 4 on the left-hand side, which is log base 7 of 3 times 4, which is log base 7 of 12, and that's what we have on the right-hand side. So 3 is a solution. In other words, it's not extraneous, it's a real solution. Question 3 is a little bit different, and the reason why question 3 is different is because one of these terms is not logarithmic. If every term is logarithmic like it is in question 1 or like it is in question 2, your strategy is to write the left side as a single logarithm and the right side as a single logarithm, and then to drop the logarithms, because if the logs are the same, the arguments must be the same. The strategy with question 3 is different. What we're going to do is move all of the logarithmic terms to one side, then combine the 2 logarithms that we have here. This is a difference of logarithms. It can be written as a logarithm of a quotient. And this is why question 3 is different. In question 1 and 2, we were able to get a logarithm equals a logarithm. Here, you have a logarithm equals a number. So in order for us to solve this, you have to convert this to exponential form. This is what's different. Remember, when you don't see a base written, it's a common log, which is base 10. And that means I can take 10 raised to the 1 and set it equal to what I am taking the logarithm of, 8x plus 4 over x plus 1. Then I can cross multiply to turn it into a grade 8 equation or a grade 7 equation. 10 multiplied by x plus 1 equals 1 multiplied by 8x plus 4. 10x plus 10 is what the left side becomes, equals 8x plus 4. If I subtract 8x from both sides, I have 2x, and if I subtract 10 from both sides, I have negative 6. When I divide both sides by 2, I get negative 3. Now, is negative 3 a solution? Well, in order for us to decide whether it is a solution or not, we need to ask ourselves what would happen if I put negative 3 in for x. When I look at this equation, on the left side I have log of 8 times x. Well, x is negative 3 plus 4. If we figure out what 8 times negative 3 and then plus 4 is, we get negative 20. Since that argument is negative, that logarithm is undefined. And what that means is that negative 3 is not a solution. Negative 3 is extraneous. And really, when it boils down to it, everybody, when you solve a logarithmic equation, you just have to make sure that the answer you get does not create negative arguments in the logarithms. Log base 2 of x minus 6 equals 3 minus log base 2 of x minus 4. Because one of the terms, 3, is not logarithmic, what we have to do is move all of the logs to one side. Log base 2 of x minus 6 plus log base 2 of x minus 4 equals 3. Now I can combine these logarithms on the left. A sum of logarithms is the product of the arguments. And now that we have a single logarithm equals a constant, we can write it in exponential form as the base raised to the exponent equals the argument. And this is pretty much a Math 20 equation. You need to simplify this. 2 raised to the 3 is 8. When I FOIL out x minus 6 times x minus 4, I get x squared. I'll have minus 10x, and I'll have plus 24. Since it's quadratic, I zero the equation by subtracting 8 from both sides, and end up with x squared minus 10x plus 16, which is factorable, into x minus 8 and x minus 2. That means that we have two solutions, x equals 8 and x equals 2. But we have to make sure that these solutions are not extraneous, because if they're extraneous, then they're not really solutions. Our equation has an argument of x minus 6 on the left. If I put 8 in there, 8 minus 6 is 2. 2 is greater than 0, which means it's allowed. When I put 8 in for x on the other side, I have 8 minus 4, which is 4. 4 is an argument that's allowed. So since I'm allowed to use 8 every place there are logarithms, x equals 8 is a solution. What about x equals 2? Well, if I were to put 2 in for x here, I would have 2 minus 4, which is negative 2, and that means this is not a solution because it's going to result in a negative argument. By the way, the left-hand side will also have a negative argument, but even if one side has a negative argument, even if you have to take the logarithm of a negative somewhere, but not elsewhere, it still makes that value of x extraneous. So in this particular example, the only solution is x equals 8 and 2 is extraneous. What this boils down to is one of two situations. You can take your equation and arrange it so that you have two logarithms with the same base, and if you can do that, then you can drop the logarithms and solve this equation instead. The other possibility is you have a term that's not a logarithm, so what you end up doing is getting a single logarithm equal to some other non-logarithm, in which case you write this in exponential form, and that's the equation you solve. So there's only two situations you're dealing with. Log equals log, drop the logs. Log equals non-log, write it as exponential. On page 412, questions 1, 5, and 8 are the assigned problems. Tomorrow is a Google Meet day, so if you have any questions regarding any of this or anything else, drop by. And again, my offer is always open. If you need help at any other time, email me anytime and I will get back to you as soon as I can with some help. In the meantime, have a great rest of the day and take care of yourselves. I'll talk to you soon.